Welcome back friends to another session of fluid mechanics and rate processes. Today we want to talk about something very interesting. Suppose as an engineer I am interested in estimating certain quantities for a certain device, then how do I go about it? Okay. So, the topic today is similitude and modeling. I want to start by giving you an example. So, let us assume that I am an aerospace engineer and I am interested in finding the drag on an aircraft. So, here is your aircraft and it is flying at a certain speed u and there is a drag on it d. So, this is the drag force. And this of course is the speed of the aircraft. Okay. The question that I want to ask myself is, what does the drag depend on? So, d is a function of what quantities? So, one thing is obvious, it depends on the speed of the aircraft. So, let me put here u. Of course, it would depend on the length of the aircraft, right. So, let me put in here length. You could say it also depends on the shape of the aircraft. I mean, I could have the same length of an aircraft, maybe it is made by Airbus, another one which is made by Boeing, and because their shapes are different, so their drags could be different. So, maybe I write here shape. It could also depend on the viscosity of the air. Okay. So, let me write down mu. It could also depend on the density of the air. So, let me put in here rho. It could also depend on the roughness of the material that I use. So, if I polish the aircraft, okay, versus if the aircraft is dirty, okay, there are maybe a lot of insects on it, there is a lot of dirt on it. So, let me write here roughness. Maybe it also depends on the altitude at which it flies. Okay. So, the performance of the aircraft would be different when it is flying close to sea level versus if it was flying at 30,000 feet where it actually cruises, and so on. So, as an engineer, when I want to design an aircraft and I am interested in estimating what is the drag on the aircraft, there are so many parameters, and of course, I cannot study them all. Okay. Some are not even, it is not even possible to study them. Okay. So, we will make some assumptions. So, suppose I fix the shape of the aircraft. So, I decide that there will be a certain shape that I am interested in, but I could change the length. So, I can increase the length of the aircraft and correspondingly its height will change, but shape is fixed. Let us say I also fix the roughness. So, maybe I will interested in very smooth surfaces of the aircraft. I could say maybe I also talk about the altitude. So, I am not going to worry about the temperature and so on. So, I am going to fly at sea level. Okay. And then my drag is now a function of u, L, mu and rho. Okay. So, this is the viscosity, the density, the speed and the length. Now, I ask myself, is this an easier problem to study? And you would still feel that this is not so easy. Why? Suppose I want to check each of these independent parameters and vary them, let us say, with 10 values. So, I decide the speed of the aircraft could go from anywhere from 50 meter per second to, let us say, 100 meter per second, and I choose 10 of these values. Similarly, I consider 10 lengths of the aircraft, 10 coefficients of viscosities, 10 densities, and so on. So, suppose each independent parameter has 10 values to be tested, right. Then we are talking about roughly 10 to the 4th experiments. So, if I want to now understand what is the effect of, let us say, change in u, change in L, change in mu, change in rho, I would have to conduct 10 to the 4th experiments, 10,000 experiments to get that information. It is a very big challenge. So, the question that I want to ask is, can I do this more carefully? In the sense that, do not look at 10 to the 4th experiments, can I reduce my number of experiments? And that is where my dimensional analysis comes to my rescue. Okay. So, it turns out that if I look at this problem in a very careful manner, then I should be able to reduce the number of experiments. So, I think this is a good time to introduce you to the Buckingham pi theorem. Some of you might be already familiar with it. So, let K be the number of fundamental dimensions to describe a physical variable. Okay. So, for example, in mechanics, K is 3. So, you have mass, length, and time. Okay. And let n be the number of physical variables in the relation where F1 is P1, P2, P3, P4 all the way to Pn. So, if I make a functional relationship between these n physical parameters, which are P1, P2, P3, P4, Pn equal to 0, then the Buckingham pi theorem says that if I call this as 1, 1 can be expressed as f2 of pi 1, pi 2 all the way to pi n minus k equal to 0, where I will write down here so I am writing here where your pi's are dimensionless variables such that they are products of the k variables plus one another physical variable. In other words, pi 1 could be, for example, f3 of the physical variable 1, physical variable 2 up to the physical variable k, and then we would choose one more p k plus 1. Similarly, pi 2 would be f4, p1, p2, pk, and this would be pk plus 2. And I could define pi n minus k, okay, that is the last variable, which is actually this function fy, which would again be f p1, p2 all the way to pk, and finally the last variable pn. So that is the Buckingham pi theorem. So let us go over it once again and try to make sense out of it. So I have k fundamental variables, okay, which could be mass, length and time, and I had n is the number of physical variables in this relationship. What the Buckingham pi theorem says is I can reduce this to n minus k non-dimensional variables, and then it gives me a recipe of how to determine them. So how do we apply it to this problem of the aircraft? So notice I have this definition that drag is a function of these 4 variables, okay. So I will repeat this here. Drag is a function of u, L, mu and rho. This I could actually rewrite as that g is a function of drag u, L, mu, rho, 0. So this is a representation of the functional relationship between d and the other 4 variables. So totally I have 5 variables. So this implies I have n equal to 5. Because I have 3 fundamental variables, which means k is 3, so the number of pi's that I need are 5 minus 3 equal to 2. So I should be able to express this equation here in simply 2 variables. It is very powerful, and I will tell you what these variables are. Of course, you could choose different variables. As you know, in dimensional analysis, you could form your own variables, but the most popular ones are the following. So there is pi 1 and pi 2. Pi 1 is typically drag non-dimensionalized by rho, u square and L square with a half in this. So, this is the drag coefficient, and pi 2 would turn out to be the Reynolds number, which is rho u d by mu, which we denote by Re, which is the Reynolds number. And drag coefficient we typically write as Cd. So, the functional relationship now is Cd is actually a function of Re. Okay, as simple as this. So, now if I want to do an experiment, this is the experiment I should do. My drag coefficient, which is actually a non-dimensional number, is a function of only another non-dimensional number, which is Reynolds number. So, this I could do in just 10 experiments. So, 10 experiments versus 10 to the 4th experiments. This is the power of non-dimensionalization. Okay. So, what we are saying is that if you are willing to work in non-dimensional variables, you can have a better representation of the physics. Mind you, the model is not changing, the model is the same, the flow equations are also the same. Okay. But if we put them in non-dimensional form, then it could in some sense reduce our work. Okay. So, let us look at this a little bit more. Let us go back to the non-dimensional equations. We have already looked at the flow equations, and what happens if we non-dimensionalize them? So, we are going to make some assumptions to make this analysis a little bit simpler, but the analysis would hold for more complicated situations. So, we will assume the flow is steady, which implies that all my terms which involve local time derivatives, they are 0. I am further going to assume there is no body force. Again, a simplification which can be incorporated with body forces, and we just want to illustrate some ideas. We will also assume that there are no free surfaces close by. So, in some sense we are only talking about submerged bodies. So, it could be, for example, an aircraft in an atmosphere, maybe submarine, okay, in water, or maybe a car on a road, an automobile or a train, and so on and so forth, or maybe a building. But we are not talking about sloshing in a tank or a ship sailing in a surface. That can also be done, but I want to do the analysis for a simple situation. So, we already know the continuity equation. It is divergence of V equal to 0. And I also know the momentum equation. I will write it for the steady state. So, that would be rho V dot gradient of V plus the gradient of pressure, that is equal to mu times Laplacian of the velocity. Okay. But these equations are dimensional. And I want to non-dimensionalize them. So, I will have to introduce non-dimensional variables. So, let me take an example. So, let us say this is my x and y axis. There could also be a z axis which is coming out of the plane of the blackboard, and let us say I am interested in this aircraft. and let us say L is the length of the aircraft, I can actually choose half the length, or I could choose the height of the aircraft. It does not matter, I just choose L to be the length that I think it characterizes this aircraft. It is something like if I choose a sphere and I ask you what is the characteristic length of the sphere, some of you may say it is the radius, others may say it is the diameter, and of course, the answer eventually would, the analysis would depend on what you choose. But if you are consistent throughout, then you can carry it through. Okay. And let us say the speed at which the flow is coming at it is u. So, this is the free stream speed. Okay. Now, what I can do is I can define x star as the non-dimensional variable, which is simply x divided by L. So, what this means is that if I had the scalar x star, that would be x by L, y star would be y by L, and z star would be z by L. So, notice I have non-dimensionalized all the coordinates with the same length scale. Okay. You could have, for example, done Lx, Ly and Lz, 3 different length scales in 3 different directions. I am not doing that. Okay. The length scale I am taking to be the same for all the coordinates. Likewise, I could talk about a non-dimensional velocity at any point. So, suppose I am interested in the velocity at this point x, then this is defined as the dimensional velocity divided by u, the scalar u, and u is the free stream speed. So, what this means is that my Vx star is actually Vx divided by u, my Vy star is Vy divided by u, and likewise my Vz star is Vz divided by u. Notice again, as I did for the length scales, my speed scale or the velocity scale is the same in all directions. Okay. What about pressure? Now, if you recall, we are talking about an incompressible flow. Okay. So, I have written these to be divergence of V equal to 0 is for an incompressible flow. In an incompressible flow, the pressure datum does not matter. I could replace this P with P plus P0, for example, and it still does not change anything. Okay. So, therefore, what I will do is I will use the dynamic pressure, use twice of dynamic pressure which is actually rho u square to non-dimensionalize P. Okay. Notice rho u square has the same dimension as pressure. Okay. So, we will define P star to be P divided by rho u square. Let me call this as equation 1 and maybe this as equation 2. So, let us non-dimensionalize first equation 1. So, non-dimensional form of the continuity equation, and let me do this in 2D just to show you how it is done. So, my divergence of V can be written as del Vx by del x plus del Vy by del y equal to 0. Okay. I could add the third term, which is del Vz by del z, but I think what I am doing here in 2 dimensions would be good enough to illustrate the concept. I now try to replace Vx, which is the dimensional velocity, in terms of non-dimensional velocity. You can see from here Vx is simply Vx star times u. Similarly, x is simply x star times L. So, I can now write this equation as del of Vx star times u divided by del of, I will replace x with x star times L. Okay. And I can do the same thing with the next term, which is Vy star times u divided by del y star times L. Y is y star times L, and this is 0. And this therefore I could write as u by L times del Vx star by del x star plus del Vy star by del y star equal to 0. And this I can write in a compact notation that divergence star dot V star is 0. So, this is the non-dimensional form of my continuity equation. Okay. It kind of retains its original form, which was in the dimensional equation. Now, let me give this equation a try, the momentum equation. So, I will try with the x momentum equation, and then we can generalize it to the other equations. So, again let me do this in 2 dimensions. So, the x momentum equation in 2 dimensions would be rho Vx del Vx by del x plus Vy del Vx by del y plus del p del x. This is mu times del square Vx by del x square plus del square Vx by del y square. I try the same trick. I replace Vx with Vx star times u, and I will replace x with x star times L. Okay. So, let us see what becomes of this equation. So, I would get rho times, the first term would be u times Vx star, and this is del by Vx star times u by del, and x would be x star times L. So, that is your first term. The next term would be u Vy star times del of Vy star times u, and this would be y star times L. Okay. So, that takes care of my convective acceleration. Then I come to the pressure term. So, P I could write as, from here P is P star times rho u square. So, this I would write as P star times rho u square divided by del x, which is x star times L. And now I come to the right hand side. So, that would be mu times this term over here, which is del square L Vx star, sorry, u Vx star. And then I had a second derivative. So, this is x square. So, therefore, I will have to write L square x star square. Okay. And then for the second term, I would write del square u v y star divided by del L square y star. And of course, I did not write the force terms, okay, the body forces, because I assumed them to be 0. Now you can see there is a u square from here and a L, so I get rho u square by L. So I will take everything out. From here also I get rho u square by L. So let me write this, rho u square by L, and I will again put it in a vector notation. So this would become v star dot gradient star of v star, okay. And then I have the pressure term, which is again I can take out rho u square by L gradient star of P star. And then the next term is mu, and I would get u by L square, and this Laplacian term I can write as, this is now the Laplacian of V star, okay. So I can take these rho u square by L and transfer them to the coefficient on the right hand side, and therefore I would get V dot plus gradient star of P star. This is, so you can see this one u cancels this, one L would cancel this. So rho u would go here to the denominator, so I get mu by rho u times L, and this is Laplacian of V star. This quantity here, some of you may be able to identify this. I will call this as 1 by Reynolds number, where the Reynolds number is defined as rho u L by mu. Okay. So kindly look at the analogy between the dimensional form of the equation and the non-dimensional equation. So for your convenience, maybe I can write down the non-dimensional equations next to them. So the non-dimensional equation would be divergence of V star is 0, and the non-dimensional form of the momentum equation is V star dot gradient star of V star plus the gradient star of P star, that is the gradient of pressure term. This actually is 1 by Reynolds of Laplacian, the non-dimensional Laplacian of the non-dimensional velocity. So you can see the nice similarity between the dimensional form and the non-dimensional form. Okay. So Reynolds number turns out to be one parameter that is the non-dimensional pi. Okay. So now you can link what I showed you for from the Buckingham pi theorem to what we are seeing from the equations. Okay. They are actually both connected. So for the case of this aircraft, I was able to show you using the Buckingham pi theorem that CD is a function of Reynolds number. That means, in terms of the non-dimensional variables, Reynolds number is the only variable if I do not worry about temperature changes, if I do not worry about altitude changes. Okay, so, I am not worried about the compressibility of the air and so on. So, the drag coefficient, not the drag itself, but its coefficient is dependent only on the Reynolds number. And you can see here as well that if I did the flow analysis in a non-dimensional form, what is the non-dimensional form? The non-dimensional speed of the flow is 1, because I would have to non-dimensionalize with this capital U. So, my incoming speed would be 1. The non-dimensional length of my aircraft would be 1. Okay, so, it does not matter which aircraft I take, as long as they are of the same shape, they all have the same non-dimensional length and the same non-dimensional speed. And in that format, I am saying that the only thing which matters now is the Reynolds number. So, that is the mathematical equations you get right from first principles, and it augurs very well with what the Buckingham Pi theorem is telling you, that if you look at the non-dimensional drag, it also depends only on Reynolds number. Okay, we will stop here, and we will continue on this topic in the next class. Thank you very much.